if we want to be allowed to use the normal approximation to the binomial, ooh, that's a horrible binomial curve, then that means we're going to be using z-scores and standard deviation, which requires means and standard deviation of the population. Okay, the nice thing is finding mean here. We don't have to add up a bunch of things and divide by a number or use all those funny formulas. If we want the mean, this comes back to the expectation, expected values from chapter 5. But the mean of the population is the number of trials times the probability of success. The standard deviation of our population is the square root of n times p times q. Now we know if we're using our normal distribution, then that has to do our standard normal curve. That has to do with z-scores. So if I want to turn a number into a z-score, I take x minus mu over sigma. From there, I should be able to find probabilities, whether I'm looking for the probability to the right of some value, or maybe to the left of some value, or maybe in between two certain values. But the extra thing to keep in mind when we're using this normal approximation, I mean, there's a number of things. Okay, I've said the phrase out loud lots of times, but the word approximation means it's not exact. Okay, we're saying we're going to save time, we're going to save effort, we're going to save computer space by approximating what this probability is. Okay, but it's not a perfectly exact answer. Okay, if I wanted the perfect exact solution, then I would have to start for Devon with 150 and do 151 and go through all 51 probabilities and add them together. But I can approximate what that probability is using my standard normal curve. So binomial distributions are discrete. Remember, when I flip a coin, when I shoot a free throw, when I draw a card out of the deck, I can be successful 1 time or 2 times or 3 times. Okay? I cannot be successful 2.7 times. I cannot be successful 12.89734 times. But when we're using a standard normal curve, this is a continuous variable. We can talk about the area to the right of x equals 3 or 3.1 or 3.125 or 3.01347. Okay, so that's part of where the approximation comes in, but we also have to use continuity correction. We have to correct for continuity. And the difference, if we forget to do that, the difference in the probabilities we'll come up with is not huge, but we're still incorrect and we're still going to miss points on a homework quiz or test. Okay, so let me find Devin again. I'm going to delete these guys. We'll either put them back down or we'll make up new ones when we get past 150. If we look at this problem and say, I don't really feel like finding 51 probabilities today and adding those 51 numbers together, even if I had a table to help me, which some of you may have learned how to use in the back of the book. Okay. If I take n times p, we get 180. If we take n times q, we get 20. And since both of those numbers are bigger than 5, we know we can keep going. If one or both is less than 5, then we're just stuck doing this by hand the long way. We need to find the mean of this distribution, which is n times p, which is the 180 we found before. We need to find sigma, which is the square root of n times p times q. So 180 times the 10th is going to be 18. Now, when I'm looking at my standard normal curve, I say I want to know the probability that Devin makes 150 or more of his free throws when he's shooting 200 of them. So 150 or more. Now, the one thing back when we were in chapter 6 to begin with is whether this said greater than 150 or greater than or equal to 150, we were looking at the same area. The area under a single point is equal to 0, and I don't know if it's been so long, got that said out loud in class, but regardless of what this symbol was, it didn't affect how we approached the problem. Okay, when we're approximating the binomial distribution using the standard normal curve, then this does matter. Okay, this says we're starting at 150, and then going up from there. When we correct for continuity, a lot of students get confused about when you add and when you subtract and what we're doing to the number, but understand that every time, once we've drawn our picture, we need to make it half a unit bigger. Meaning, while it's not possible for Devin to get 149.5 free throws, if we were to make this a continuous situation, okay, he could make 149 or he could make 150, but we have to pretend like he can make anything in between. Which means if we're talking about 150 and bigger, then anything from 149.5 and up would fall into this category. So when we're down here finding our z-scores, x minus mu over sigma, we don't use the 150, but our continuity correction factor says we're going to start at 149.5. Okay, minus mu over sigma. And then we're going to, when we type it into our calculator, we get negative 1.69. So 149.5, my picture is bad here because I wasn't paying attention. 150 is less than the mean. The mean is in the middle. Apologize for that. So the 180 is here in the middle, which means if I want to make 150 or more, I'm over here. Okay, but then if I'm going to correct for continuity, I'm at 149.5. Okay, so to the left of 180 means I'm going to have a negative z-score. If I want to find the probability that Devin makes 150 or more free throws, when I correct for continuity, that means I'm looking at the area to the right side of 149.5, which means I'm looking at the area to the right of z equals negative 1.69. And if we are looking for the area to the right of that z-score, we need to take 1 minus whatever that table says. So I left my note card across the room. I'll pause it and be back. You look it up while I'm gone. And so that's 1 minus 0.0455, which is 0.9545. He has over a 95% chance of making at least 150 of those free throws. I'm going to pick up, we're going to stick with Devin in this situation. We're going to do some other probabilities, but I'm going to make a new video for that so this doesn't get overly long.